our jingle.
This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hi, I'm Lee Bortons. It's Wednesday, April 10th, 2024. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss 2 lessons each week from our math curriculum for families with students enrolled in classical conversations communities. Notice I took out the coming soon because it's all happening. So thank you, team, here for just all the encouragement you gave us. And Kirsty, maybe as we go on, you can update us a little bit on what's available. But meanwhile, we're nearing the finish line in our second pass through all of the booklets before we begin our summer schedule. So Kirsty, why don't you let us know what's going on?
Excellent. Yeah, we are close to the end of our year, our rapid tour through, and we're going to be talking about lesson 27, complex numbers, and lesson 28, proofs today. And I just want to say they're at the end of the year when a lot of us are starting to maybe lose some of our motivation and get a little bit of spring fever. And the lessons were designed with that in mind, that Lee recognizes, right, that's sort of human nature, that's going to happen. And so she's designed these intentionally to draw your student in with lots of repetition of the ideas over the course of years. But there's a lot of meat in these. And as we were just talking yesterday about what we were going to discuss today, we both agreed that there's a lot of big ideas. So hopefully we're going to touch on a few of those today and get you all excited to finish your year well. So here, of course, just like we do in our challenge communities, we're going to take our time to look at the math map and identify where we are. We are still primarily talking about the naturals level. That's what we are working through, the naturals level, although we're trying to give you some ideas of how you can even use the naturals level with older students. And we are on lessons 27 and 28. So those are across the bottom, just to give you that reminder every week of where we are in our math journey, where we're headed next. Are there any lingering questions before we jump to lesson 27?
Do you know what you're going to do with your book club after we finish this? Maybe you've already said and I missed it.
We do know what we're going to do, and we are going to keep on going because we know that this is the primary way that families have of interacting with Lee and I and asking those math questions and talking about math. So we will continue. There's a couple of weeks we're not going to meet. We're not going to meet May 1st because that is the a week of all the events here in Southern Pines, National Memory Master, graduation, the conference. So we won't be meeting that week, and nor will we be meeting on January the 3rd because it's my anniversary. No, really, we're going to be taking off January the 3rd because we know a lot of people are oftentimes very busy around the Independence Day holiday. But other than that, you'll be able to find usually both
Kirsty,
of us.
did you mean July 3rd? You said January.
Yes.
July 3rd.
Yeah, I really meant July 3rd.
Okay, good.
One of those J's. July 3rd. But other than that, we will be here at 1 o'clock on Wednesdays. We are going to change our format a little bit over the summer to go a little bit broader, and we're going to look at each of the dimensions in turn. So instead of going lesson by lesson, we're going to go dimension by dimension. You can bring questions from any dimension. Our goal really is that over the summer, that this time is going to be time for you to bring your questions and your ideas, things you want to share, and contribute to that conversation. But we'll have a few things that we've prepared just in case everybody shows up with nothing. So we're hoping that that's not the case, but we'll have some sort of big questions, those dimensions, and we'll just hit those dimensions probably 3 times each over the course of the summer. And then in August, we'll look at our next iteration of the book club. So yeah, so please continue to come back week after week and join in the math conversation with us.
Sounds great.
Are there any other questions?
Kirsty, I have a question actually. This is my first time attending. We have community days on Wednesdays, so I've never been able to attend. So I'm really excited to be here. I have lots of questions. But one question that I was kind of thinking through this morning as I was looking at the material, and maybe you cover this in previous videos, but I'm only about 4 or 5 videos in, so forgive me if that's the case. But these Invention and Memoria pages that I'm seeing in the complex level, are these the same in each level?
Yes, they are the same in each level. The goal of those pages is to bring in ideas. So on the left-hand side, you're going to frequently see us pulling ideas from multiple dimensions that have to do with a similar topic. So you may see some previews of ideas or reviews of ideas. And then on the right-hand side, the goal is to look at some of the memory work that you may want to work with your student, where the flashcards are doing that out of context. That Memoria page is designed to help put it in context. And so, yes, those will be the same each year. There's not pressure on you to try and like memorize those pages as you go through.
Okay, so I can use my complex to inform what I'm physically working through in the naturals right now then.
Yes.
Okay, great. Okay, I literally had that question and then thought, wait, it's Wednesday and it's like 10 minutes before the math club. I can actually ask it live. So that was pretty cool. So
Yay,
thank
well,
you.
I'm glad. Welcome. I'm glad you're able to join us.
Thank you.
All right. Well, let's go ahead and jump in to lesson 27 and let's take a minute and as we do every week and see what might feel familiar or what looks unfamiliar to you.
So the triangle is familiar, maybe even the 45-degree angle. Some of the other things might not be as familiar in that triangle in the top right corner.
Okay.
And this is probably our first page where almost all of it may be unfamiliar to someone who didn't get to study calculus. Okay.
I literally did this with my 12-year-old again this morning. But pretty much what Lee just said, it was very unfamiliar, but we kind of walked through things that might have looked familiar in the middle on the left, you know, a number plus an unknown. We just treated I as an unknown, where he's usually used to seeing X. So
That's perfect.
And
That's
some
a
of
good
that,
way to begin it.
oh, yeah.
Good.
Some of that is familiar just from previous lessons, like R, I would assume is still radius. It looks like it is, equals, and then it says what theta equals. And we know those are the coordinates we've been using for polar graphing. But that's CIS in the middle, that's new. And there's other new components, but there's kind of like this basic pattern that I recognize from other lessons.
Excellent, Jana. So that's great. And so I love what you just said, because you said I was able to recognize some things from previous lessons and some patterns, right? Because that's what when we're talking about being mathematicians, we're really talking about patterns. And so being able to recognize that and go, well, R usually is my radius, theta is usually my angle. So I'm going to start there. And now I see this cis thing that I'm less familiar with, but I'm going to trust that that's going to unfold what it is. But I see where the square root of 2 and the 45 go in, and that's giving me coordinates. So great job in taking what was familiar and connecting that to something that was unfamiliar and making an educated guess about what it was. So well done. So while we're on this page, I thought we would take a minute just to talk about how different domains, different levels of students may approach one exercise. So look at that middle right section where we have all of our i's and our square roots of -1. And if you were doing this with your 6-year-old, your natural student, how might they make this matching happen? What might they match?
The amount of i's they see, or the amount of negative ones they see to the exponent.
Good.
Or
Just counting. Yeah, excellent. So if I had a real student, what might they recognize?
A real student as opposed to an imaginary student.
They might recognize that this square root times the square root gives you what's inside of it.
Okay, so they might do that. What about that notation on the I? What does that mean? Do you think a real student might recognize what that means?
Oh,
What does that mean?
The I itself?
Like, well, right when I have that 2 next to the I, what is that 2
Yeah.
telling me? What operation is that?
The exponent, yeah.
It's squared, yes. So yeah,
Good.
I
So
was gonna say that they would
Right,
see the 2, the 3, and the 4 and see the number of square root symbols there and match those.
okay, good. So our natural students might count and just go, I'm just matching 1 to 1, 2 to 2. But my real student now, that's a sort of a 10, right? My real student might say, oh, that's the first power of I, the second power of I, the third, the fourth power of I, that's exponentiation. And so that's telling me how many factors there are. And on the other side, I'm multiplying and I have these different factors. So they might recognize not just counting and matching the number, they might actually recognize the operation. Now, how about, and here you go, Jana, right? I had a real student, now I've got a complex student. How about my complex student? Do you think they might
That's us.
interpret this? There you go. Could they maybe recognize this differently based on the work that they've been doing, especially if anybody here has worked through the complex of some of our pilot families? Is this a pattern they've seen before?
Well, in fact, at reels and on the whole way through, they're encouraged to memorize it, but you kind of expect it around reels. And as they move into complex, if they don't have it memorized, or I should put it positively, if they do have it memorized, it makes all the lessons a lot easier if they understand this pattern. But you don't really need to understand it because it actually is written for you that I squared means there's 2 of them. That doesn't mean you really understand what's happening on the right, though.
Hmm.
So
I
our
was thinking-
complex, go ahead,
I
whoever
was
that
thinking
was.
maybe a complex student would associate, okay, well, I is the square root of -1. And so they could see the equation between those two, the symbols on the right and the symbols on the left, and what is happening with it with the exponents.
Right. So all of our students, so every level has lesson 27, right? So every lesson, every level of student is going to be interacting with imaginary numbers and complex numbers. But our complex students are doing that all year long. They're really immersing themselves in complex numbers and operations in complex numbers. They're going to have spent quite a few exercises, right? The time of quite a few exercises memorizing this pattern and examining this pattern. And so where my natural student maybe is just counting, my real student is recognizing exponentiation, my complex student now is going, okay, well, I know that this I is the imaginary number and I know what this pattern is. And so that's just, I wanted to point that out as that example of sort of how we can scaffold right throughout the years with one, even if it, and the example will be, the exercise will be a little bit different, but as we look at that exercise over the course of many years, right, our different students are going to understand it differently. And so I just thought that was a great opportunity to talk about that. Let's go ahead and look at page 2. And how about on this page? What are some things that are familiar and things that are unfamiliar?
Sine, cosine, and tangent of theta is
Good.
familiar. We've seen that before. The hypotenuse, opposite, and adjacent at the bottom. And then the polar coordinates, yeah, kind of, but you know, at least known.
Good.
they spent a lot of time the first 8 weeks doing imaginary number axis all by themselves and then real axis all by themselves, and now they're combined.
I think the degrees on the polar axis are familiar, but using a 4 instead of a 1 because
Yeah.
they've been using the unit circle a lot is new.
So I love the fact that you're all going, oh, I remember this from other lessons, right? Because I really, there's just so much built-in repetition of ideas within the year. And we see how these lessons are going to pull from things that we've experienced throughout the year, and bring them together, sometimes in new ways, right? So we're looking at some ideas here, and we're looking at it in a slightly different way that's going to both help us to understand complex numbers, but it's also going to help us to understand the trigonometry a little bit more by the way that we keep looking at these things. So here's a question. When you look at the top and it talks about complex rotation, if we were just in 1D, I'd like you to just think about being in 1D. What happens when you multiply by -1?
Reverse directions.
It reverse my direction, right? So if I was looking down my positive number line and I multiply by -1, I go to my negative number line. Right? If I was on my negative number line and I multiply by -1, I go to my positive number line. So now imagine that in 2D, so now you can actually see me reversing. How many degrees did I go?
I don't know.
180.
180, right? So multiplying by -1 gives me 180-degree change. If I multiply by 1, what happens?
You don't move.
It doesn't look like I moved, does it? But could I have, let me give myself some space here. Could I have gone
Yes.
360 degrees?
Or 2 circles around or 3 circles around.
Right. All right. As long as it's a multiple of 360, right? I end up back where I started. So is multiplying by -1 kind of like half of multiplying by 1? Half of the process?
Yes.
Yeah, right? If I go 180 degrees, I've multiplied by -1. Now I go 180 degrees. I'm multiplying by another -1. Times -1 gives me 1, and I ended up back where I started, right? So now think about this. I'm here on my positive, and I only want to go halfway. I want to go 90 degrees. Is that halfway to -1?
Yes.
Yes. So what could I multiply by? Where I would be multiplying, if I multiplied, what would I multiply twice to get to -1?
An imaginary
I?
number.
Would it be the 90 degrees 2 times?
So I'd go, well, yes. So if I was going here and then here, I'd multiply by the same thing twice. And so somebody said the imaginary number. And what does that represent?
Right.
The square root of -1. So if I have the square root of -1 times the square root of -1, I get to -1, right? So I only want 1 out of those 2, right? So I'm kind of going halfway. So now I'm going 90 degrees. And am I looking down my line anymore? I'm looking in a new direction, right? And that's my imaginary axis.
You
You
can
just
see it
blew
on
my
that,
mind.
but you can see it on the page where she has 4 on the positive, and then to get to the top at 90 degrees, she had to multiply it by I.
Right.
Where did that 4 come? Is that just the 4?
It's just,
because
yeah,
it's
it
on
could
the
be any
XF?
number.
Just so
Yeah,
you know, this picture's been redrawn with a tick mark so you can see it's labeled better.
it could have been any number, right? So if I take
Okay.
any real number and I rotate it 90 degrees, I'm going to come to that number on my imaginary axis. And then another 90 would get me to my negative axis. Then I'd be on my negative imaginary axis, and then I'd come back around to my real axis. So
So
all it's, go ahead.
if we didn't know what that real number was, then we can use the letter R, correct?
Yes.
Okay.
So now here's the next question, just to make another connection here for you. If I was to write, this is going back to lesson 7, so see if anybody remembers. If I wanted to write the square root as an exponent, anybody remember what exponent means, the
It's
square
to the
root?
1/2. It's to the 1/2. Oh my gosh. I love this.
And for those of you that didn't get it, next year you will.
Melba got
Oh.
it, right? So there you go. So when we think about complex numbers and multiplication, we're always going to see this rotation, that multiplication is giving us some kind of a rotation. And when we're dealing with real numbers, because it's just on my number line, my rotation is either 180 degrees or 360 degrees, so it gets hidden. But as soon as I start multiplying in my plane, then I start to see that rotation a little bit more. And just recognizing that where that comes from, I think is a fun activity. And you can do that at home with your kids, right? Tell them, okay, positive, now negative, now go halfway. Right? And where are you?
Not on the real number line. That might be their only answer. Good, Kirsty. That was enthusiastic.
Okay, well, it's fun. Well, let's look at page 3. And page 3 is where we've got some complex operations going on. And we haven't really talked about the fact that these complex numbers are two-dimensional yet. So let's take a look at the fact that our complex numbers are two-dimensional. They have 2 parts. And so this goes back to lesson 2, even for our little kids. What 2 parts does a complex number have? Anybody remember?
Real and
Real
imaginary.
and imaginary.
Real and imaginary. Could my real part be 0?
Yes.
Sure,
Yes. Could my imaginary part be 0?
probably.
Said with such confidence. Yes. So are all of my real numbers complex numbers?
I think so. Is that more
They are.
confident?
They are indeed. So all of my real numbers are complex numbers, and all of my imaginary numbers are complex numbers. And what that means is that when I define something for complex numbers, I'm saying it's true for all of my real numbers as well.
And if you remember, week 2 has that Venn diagram where the domains are nested to show you what they mean, as well as I2 with the map across the top.
So now if I want to add, because remember way back in lesson 4, well, 3 and 4, we really emphasized when we were comparing or adding or subtracting, we had to have like terms. So if I wanted to add 2 complex numbers, what are the like parts?
The real parts are alike and the imaginary parts are alike.
Excellent. And which part is my horizontal and which part is my vertical?
Your horizontal is your real and your
Real.
vertical is your imaginary.
Great. So we can see, looking at the top of page 3 here, we can see where these numbers are identifying a point in the plane, right? And so that's where I find them. And here's the key thing, that even though we have to represent them as a sum, such as 5 plus 2i, they are one number. right? It is just one number, which means I can operate on them like a single number, right? Instead of having to have two numbers for that location. They are just one single number. And we were going to point out that if you look at the exercise here, that if you look at that and think that maybe it's confusing exercise, it has been changed and updated to clarify there how those parts are combined, that it is the reals with the reals and the imaginaries with the imaginaries. Because on that second line, it's been the reverse of the distributive property to pull that I out so that we can show that form of a plus bi, right? So a is the sum of my real parts and b is the sum of my imaginary parts.
So that's something we've done over the past years. We went through the lower grades in particular, and this problem is a perfectly fine problem, but their eye won't know how to follow it because the twos are used two different ways. And so that would be changed to something like 5 plus 2i plus 7 plus 3i, so they can follow it in the next step. So those are the kinds of things that we think about the pedagogy of what we're doing, not in the age group we're working with, as we clean up the problems for the release.
I have a question. I understood that part when I was doing it with my son. It's when we got over to the graph. Did you just label the y-axis I and the x-axis R? I don't remember that part from the other ones.
So it looks like we've changed the labels. They are different because, and here's why they're different. If it was X and Y, when we're graphing with X and Y, X represents one set of numbers, Y represents another set of numbers. And so they're two independent numbers that then we use a function or a relation to map between the two sets. But they're actually two separate sets of numbers. And while the reals and the imaginaries can be looked at as different sets of numbers, when we add them, we're making one number. It's not a relationship, it's not a mapping from the reals to the imaginaries, right? So I would never put a function on here. I would never put a line on here and say, this is how I go from real to imaginary. They're both independent and they just give me the coordinates for that point. So it's a little bit different to an X and Y graph, but our imaginary and our real axes are always going to be perpendicular to one another, where that real is giving me my horizontal coordinate, that imaginary is giving me my vertical coordinate. And so where they meet, that is going to be my point. So here, let me pull my drawing tablet out real quick. I should have that ready.
Well, yeah, I can see the 5 real and go up for 2i for the first parentheses. And I can see the 7 and the 5i. And my mind wants to see the 2 plus 3i as a separate point, but that's probably wrong, right?
You see, okay, so 5 plus 2 is 7.
Yes.
And 2 plus 5 gave you the 3. Yeah, so go back there and explain about your lines. This threw me for the longest time. I had to ask her over and over again. What do you mean there's no lines? There's just points. What do you mean there's not two numbers related? There's one. So it takes time.
Okay.
So
I'll
there's
get there.
my 5. There's my 5 plus 2i.
Right.
And I'm going to just do different colors. My 2 plus 3i would actually be, here's my 2 and here's my 3. There's my 2 plus 3i. When I use vectors, I can take that vector and it's defined from my origin as 2 plus 3i. And so it goes to the point 2 plus 3i. But the beautiful thing about a vector is that it is not location specific. So I can pick this vector up and I can move it anywhere I want to. And so I can move it from the origin to right here. And so that's here's my 2, here's my 3. All right, here's my 2, there's my 3. And it gives me a way of illustrating that addition and helping students see how I went from, found my first number. Now I've added my reals and my imaginary parts. That's my second number, but it came from here, right? This is that number. But because I'm illustrating it with vectors, I can move that around to show that addition. Does that help, Carrie?
Oh, it helps huge. I'm going to use a color coded on mine too. So I like the color coding.
I've done this with some of my groups, and it's hard to think about adding those together. And we've talked about, let's say you're in the woods, and I tell you to take 100 steps to the northeast, and then turn and take 20 steps, in a different direction. Where did you end up? And so that's similar to what you're seeing there. Does that work, Kirsty?
It does. And if you think, even if you just think in 1D, right? Let's go back and just think one-dimensionally. Right, here's my origin. And 1, 2, 3, 4, 5. Okay, so here I know that when I have 5, here's my 5, right? Well, 3 is actually defined from the origin, right? Here's my 3. That's how long 3 is. But when I add it, I don't go back to the origin. I start at 5 and I do my 1, 2, 3, or my 3 vector. And I realized now it was actually 2 that we were doing there, but and I end up at 8. Right. And so it's that same idea here. It's just that when it's in 2 dimensions, we tend to kind of like, oh, this looks confusing. But if we go back and look at how we added in 1D, right, we always started with our first number and we moved from there. So that's all we're doing here is we're saying plot my first number, then this is telling me 2 to the right, and then 3 up, which is going to take me to this point. And now my resultant vector is the answer, right? And that's this one. And so now I can look and I can go, okay, well, that was 7 and 5i, which happened to be 5 plus 2 and 2i plus 3i. So.
It's so interesting to me that you can have a vector that goes to this spot and then another that goes to this spot, but the two of them combined can equal a line, I guess it's not a line, but a vector that has a shorter, it combines to be the same. I mean, I see it and I do it and I'm like, okay, got it. But the physics of it is interesting to me.
I was going to say that the transcendentals, I'm glad you mentioned vectors because that's what they saw. They saw vectors and they see the resultant vector and looking at the graph.
All right, we probably need to move on, Kirsty.
All right. All right, quickly looking at page 4. I'm not going to talk too much about this page because we are past our half-hour change to the next lesson. But I just thought I would take just 2 big ideas that are related to this. One is the idea of iteration. And I already used that word when I talked about our next book club. So very quickly, does anybody want to talk about what iteration means? Kathy, I know you could talk about iterations, working on the Latin curriculum. How many iterations of the Latin curriculum have you been through so far? Right. So that idea of iteration is doing something again and again. And so when we think about, because we're talking about these numbers that are in a plane and I just wanted to address that because remember a minute ago, I said we had our X and our Y, we could map from one to the other. We can't do that with complex numbers. And so what we end up doing is we have something called an iterative function, which means that I can map back into itself and I do the same thing over and over again. And so we're going to just take a very brief look at that over the course of 13 years of what that means to prepare students, right, for some of these patterning things that they're going to be seeing outside of the math map. And then the other thing that they're going to notice in this lesson is an idea that we introduced back in lesson 8, right? And that's talking about the number of nth roots. So how many eighth roots would any number have? Anybody want to have a guess? 8. And how many 52nd roots would a number have?
52.
52, right? So this is a lot of times we don't always see this because how many roots, how many third roots of 8 are there?
3.
Roots. 3.
There are 3, but what are we sometimes tempted to think of? That there's just 1, right?
Negative.
Because if I said the square root of 4, a lot of you would go, oh, well, there's positive and negative 4. But if I said, what's the cube root of 8? If we're just thinking reals, then we think there's just 1 and it's 2. But really there's 3, and complex numbers are going to help us to understand where those other 2 roots fall. And so that's why we're going to look at roots again in our complex numbers, because a lot of times those other roots don't actually fall on our real number line. They fall in our complex plane. And so I won't go into too much detail that you have to like wait and get excited to read more in the curriculum or come back over the summer. And that goes along with that idea that if I have an nth degree power sum polynomial, like an x to the 8 plus something, something, something equals something, that there are going to be 8 roots, right? And it's all related to the same idea of numbers. All right, moving on, briefly pausing here just to let you know that we are now looking at the calendar. We are 2 weeks away from the complex lessons being on sale, and they will be on sale for 2 weeks. So certainly if you're planning to purchase the complex, we want to encourage you to get those orders in during those 2 weeks. It's a significant sale. Your product sales specialists are continuing to do their intro, both the Experiencing the Math Map events, but they're also doing their private sales calls, especially with Rising Challenge A parents. I know that they have some coupon codes and that there is a deadline on that. So if you haven't booked a time with your PSS, now would be the time to do that. The companion is on CC Connected now. And so that will, there is a little preview available that anybody can see, but that will be going away shortly, and it'll be just for people who have then fully enrolled for 2024. So we just want to encourage you, if you want to be able to continue using that, you need to be enrolled for 2024.
I have a quick question.
Sure.
About that. So we're in New York and we don't have a project sales specialist. Is there anything that my incoming Challenge A families can do to meet with anyone or get in on some of these sale opportunities?
So I know that there are a couple of product sales specialists on the call. So I'm going to pause for a moment and see if anybody that's on the call that can answer that question could maybe jump in and either answer that or get in touch with Kelly to help her and her families. Is there anybody who can address that?
Yeah, I would encourage them to check with their SR, their support representative, and their area representative, because they can connect them to some of the product sales specialists that are nearby. And then of course there are product specialists that are doing online things, and those families in New York would be able to hop on some of those calls. So connect with your leadership to connect you with those local things.
We have brand new SR and AR in our area, but I'll see if they can help figure that out.
Kelly, if you can't get an answer, I would definitely encourage you to go ahead and email the math map at classicalconversations.com, and Shauna and Babs are our curriculum assistants, and they would probably be able to help connect you with somebody if you're not able to get an answer.
Thank you.
So through the companion, you're also going to be able to see these digital versions that are starting to roll out. And we're going to have available this year the digits, the naturals, and the fractions. And so For those of you who are looking to prepare for Challenge A in the fall, we certainly encourage everybody to start with the naturals. Or if you have students that are younger, we're encouraging everybody to start sort of with the one step down from where you are, or two steps down from where you are, like step down versus stepping up. So if you had an 8-year-old, we would recommend you look at the naturals. If you had an 11-year-old, the fractions. And then the next year, when we have both physical releases and additional digital releases, those lessons, those students would be able to slot into the age appropriate lesson next year. So that is how we're recommending everybody start in that wants to get started this year. All right. Any questions on the rollout or the curriculum and where things are right now?
I have another question, Kirsty. When you were speaking about the companion and you said that families need to be fully enrolled, when you say that, do you mean that they've paid the application fee and the enrollment fee, but not necessarily the tuition, or does the tuition also need to be paid?
So it's like the week 7, right? So however it's attached to however you explain it to your families now, right? When you get your full access to CC Connected, you know how you kind of get your 6-week preview and then you get the full. The companion is tied to that 7th week. And so to get access to the companion, they need to have access to the full CC Connected, which I think involves tuition.
Okay, I think you're right about that. I think that's tuition. Is that also the case for directors?
That I do not think is the case. I think directors should have access right away. Yeah.
Okay.
Yes, we do.
It's and for your families, it's the enrollment page that you as a director go into and click tuition has been paid. It's a little green check mark that happens when you edit, and that's what opens it up for the families.
You said, I'm sorry, you said enrollment has been paid or tuition has been paid?
No, it's a tuition. It's the enrollment page,
Okay.
but it's the tuition column that needs to be checked that you've received their tuition. You check a box and then that opens it up for the family. You as a challenge director have access as soon as you sign your license, then you have the access to the companion.
Okay. I need to talk to somebody later about that because I don't think I actually do. Okay.
Is this program specific? Can I ask that question? If it is program specific, like for instance, if I do not have a child.
No, it's available to all CC members once they've paid their tuition for 24-25. They do not have to just have a student in Challenge A. They could have just foundations, or they could have just challenge, upper challenge, but they will have access to the companion on that week 7. Once their tuition is paid, the directors marked it. They'll be able to engage with the material and resources there.
Can you tell us where these are located on CC Connected? Like both, I tried to find fractions where we could access that and where the companion is.
It is. So when you go into challenge, put in your search box companion and it will populate in 2024 for your 2024 academic year in CC Connected. You put companion in there and it will populate. And then you'll see that digits and naturals and fractions are uploaded for you to download in their beta versions. And then complex, of course, is in its interactive state.
But where are those?
So when you go into the companion, you're gonna see like the title screen, and you're gonna like click in the top right corner to open it, and you're gonna see on the left-hand side of your screen, you're gonna see a copy of the math map. And when you hover over the fractions, you're gonna see a little button pop up, and when you click on that, it will open up those lesson pages.
Okay.
Yeah, so we are making it so that you can access everything through the companion, so it becomes a one-stop shop for you.
Okay, because I see the beta, I mean the naturals in outside of the companion, but okay. All right, so I just look for the companion first. Okay,
Yeah.
thank you.
You're welcome. All right, let's go ahead and move on to lesson 28. And this is about proof. And so I thought I'd start this off by talking about the difference between a math proof or a logic proof and a scientific proof. Does anybody want to chime in, especially anybody who's done logic and challenge? What's the difference between the two?
One is inductive and one is deductive.
Great. So which one is inductive?
That would be scientific proof.
Scientific proof, right? And so that says I find lots of examples, and the more examples that I find, the more confident I am that I am right. Whereas a math proof is deductive, it's logical, and it takes all of my reasoning. And if I can show this line of reasoning is true, then my conclusion is always true, right? So a little bit different use of the word proof, right? When I want to prove something to somebody, having evidence, right? That scientific base is that kind of evidence based, whereas math is argument based. And so just helping students to see the difference. It does not matter if I find a million different numbers that satisfy some criteria or behave the way that I want them to. That is not enough to prove something mathematically. When we think about things mathematically, we always have to be able to show how we started with one argument and then connected all of these ideas to get to what we are trying to demonstrate is true. And the other thing that I was going to ask is, does anybody on our call know what QED stands for and what it translates to?
Quod erat demonstrandum or something like that. We use it at the end of logical proofs to say, and this has now been shown or something like that.
Excellent.
That's close.
Yeah, it's that which was to be demonstrated, right? So this is what this is what you wanted me to show, and I've shown it. That is your statement that you have done what was asked at the end of a proof, QED. So we have adopted that, right, at the end of our proofs, that it's a way of saying, there you go, I did it. And I'm celebrating it. I've done what you asked me to do. All right. What I was going to talk about on this page is if you look at the top where the not the very top title bar, but one line down from there, it says constructive proof theorem 1, alternate interior angles. So we chose 15 different proofs. Most of them are geometric in nature. We chose 15 proofs that we said these are worthy of students memorizing. And because they're good things to have memorized, they're good grammar, but also because by memorizing, they're going to, and let me back up and say memorizing is maybe not the best word because the goal isn't that they memorize them, but they're going to see the same proof year over year over year. So by the time they finish the math map over the course of those lucky students who can start with digits, they may have memorized these proofs, right? If they have, then that's great. But as they become familiar with these proofs, they are going to gain that sense of, okay, this is the flow of a proof, right? Because it's familiar, because I'm seeing the same thing over and over again, I'm building up that memoria of the flow of a proof as much as I am the content of the proof. Proofs are really a rhetorical skill. And so we've tried to break them down here to, one, identify some grammar that they need to practice. So as you look at this page here, we're talking about alternate interior angles. And so we're giving them some related grammar to practice. As the years progress, they're going to start progressing to seeing more and more proof-like things and then eventually writing their own proof, right? And so they're practicing the grammar that goes into that. And we're also treating the proof itself like grammar, learning that structure, learning how to put those ideas together. So that eventually, as they gain that familiarity, hopefully eventually they will become rhetorical in writing proofs. But we've really tried to make this approachable through that grammar dialectic process for students, if that makes any sense. So the top proof on every page is going to be the same from year to year. When I say the same, not the exercise itself, but the same proof that we're building up towards. So any questions on that? I feel like I didn't necessarily explain that super well. So if you have questions, please go ahead and ask them. All right. Looking at page 3, again, you'll look at the top and you'll see it says constructive proof theorem 2. So every year, this top is going to be having to do with right angle congruency. But this page also has proof by contradiction on it. And so what are some fun ways, especially with younger students, that you could explore that idea of contradiction?
Well, it's kind of fun to talk about what things aren't. Is it, right now in the Pacific Northwest, it's actually sunny. So it's kind of fun to go outside and talk about what isn't happening outside. Is it raining? Is it not doing something?
Good. So it's sunny, so it's not this, right? So not always, but sun and rain tend to be contradictions. So that's fun, right? So the weather contradictions. What other contradictions might you explore?
A double negative. I'm not going to give you candy.
I was just going to say that because as in challenge, we do discuss this in our analogy book.
Yes.
A double negative. And because of the timing, we will have gone through that in analogies already. So that should be familiar to them.
Yeah, those litotes are fun, right? Like he wasn't not unhappy. So what does that mean? Right? Good. So double negative. So there's a lot of fun ways that we can explore contradiction with our students in order to help prepare them for the idea of proof by contradiction. Let's look at page 4. And this here is looking at proof by induction. And so let's go back to the beginning where we talked about that scientific proof being inductive reasoning and our mathematical proof being deductive reasoning in general. Here's a case where we actually have a mathematical proof that is designed for inductive reasoning. Not necessarily scientific evidence, but when we do have numeric evidence, those cases where we say, I've got 1,000 examples that this equation always works. The inductive proof is a way to take that and say, okay, I have all of these examples. I'm pretty sure this is the pattern, and I'm going to prove by induction that that pattern is true for all numbers. So it doesn't work for science, but it does work for math and for numbers. And so we're going to see that inductive proof is usually when we're dealing with patterns with numbers. And so it connects to that idea of inductive reasoning, right? That I've seen a pattern. Oh, I think that every time I look at the next number, I'm adding 2. Oh, well, if I add all of these up, I think that this equation would tell me what my sum was. Well, now let me see if I can prove that that's true for all possible numbers. That's inductive reasoning. It's working off of a pattern. Our geometric proofs are most commonly our deductive proofs, and they come from deductive reasoning. I'm going to start with something I know is true, and I'm going to link all of these other ideas together to show that something holds all the time, right? All of these things are true. That's going to be more like our logic proof. Inductive reasoning and inductive proof, I think, is one of the hardest things that you can do in math because you're making these statements that are true about all numbers. And so we're going to really try hard to give students a very gentle introduction to the idea of inductive proof. But let me tell you that if they go into math and they already have an understanding of inductive proof, they are going to love life while all of their classmates will. So it's not a huge deal if kids don't get it, but anybody that wants to continue on in math, if they do, like, they're just gonna be so excited. So, all right, so we've got a couple minutes left. I know I went quickly through those last couple of slides. So go ahead, and if you have questions about those things or something you'd like to share, maybe about your own experience with mathematical proof, please go ahead and jump in.
I guess the one thing I'd like to make as the connection is that Kirsty went through Euclid's first book of proofs and summarized in her charts the ones that we were going to use after figuring out what was the 15 that were the most important. And so this is where we don't use the word Euclid in the lessons themselves, but this is where the historical context was informative to the curriculum. And so if you ever take a Euclidean geometry course, you know, in the summer when your child's a genius, go do that. And then you'll be able to say, ah, the chart has all of the theorems, axioms, and propositions I would ever need.
Is that in the public domain by now?
Euclid is, yes.
If anybody's interested, Hillsdale has an 11-part really short series on Euclid by two very approachable math professors, and they have a really well put together translation of Euclid's work as well, broken up by books and very detailed. So
that's
it's
good
just something.
Yeah, because one of the things I like to encourage parents who feel like their children are advanced is still don't rush them through the spine, because you might be missing things or not setting them up for success in 2 years from now. And so if they are advanced, stop and go ahead and take something that's like that. Look at Gaussian geometry, or go work on topology or some other math topic that, you know, that uses just everything uses basic arithmetic, whether you notice it or not. So thanks for that heads up. I think that's a better thing to do in the summers than rushing into the next domain.
Well, while anybody's thinking of a last question they'd like to ask for this week, next week is lesson 29 and lesson 30. And we are going to be talking about really how does the Math Map year wrap up? And we're going to discuss our Seeing the Unseen booklet. That is the goal of the Math Map, is to help families to see the unseen. And so we're going to talk about the Seeing the Unseen booklet, the resources that are in that booklet, and the purpose of that booklet. And then we're going to wrap up with our final booklet, which is called Reflection. And it is where our mid-year blue book was called Assessment, right? Where do we need to course correct mid-year? Our final booklet is called Reflection. And so we're going to be talking about what does that mean to reflect back on your year and see where you grew, or maybe set goals for the following year. So that's what we're going to be talking about next week. Probably next year at some point too, but next week. And then after that, we will be transitioning to our new format of the book club, where we're going to be a little bit less rigid in our structure, a little less structured, and really inviting you to bring your questions, and as we work through our dimensions over the course of the summer. All right. Any last thoughts? All right. Well, thanks everybody for being here today. And Lee, we're praying baby to arrive. And all right.
Thanks,
Thank
everyone.
you so much. Thank you. Thank you.
Thank you.
Thank you.